welcome to Geography Program. Okay, so this is our second speaker, right? We remember. So this, I think this activity we have 6 speakers, and the second one. And today I'm very pleased to introduce our speaker because, as many of you know, Xiaolin was my former PhD student here. So today is kind of inviting me back to the department. Xiaolin is currently associate professor in the Department of Land Surveying and Geomatics in Hong Kong Polytechnic University. And he started his PhD journey here from 2010, 2014. Sounds like almost 10 years ago to the department. And I want to highlight some of his, experience at OSU geography. I just hope to thank you. Do you still remember the Appalachia, Ohio Forest Research Group? That is a research group involving 4 faculty members, me, Katie, Indra, and our former chair, Carla, and the graduate students. And Xiaolin was one of the major players in the motion component of the project. And he helped us to develop innovative remote sensing products to monitor the forest recovery in southern Ohio. And Xiaolin was a very successful PhD student here. He actually won several, very prestigious awards, including the Miller Award, which is the outstanding graduate student in geography. Also, the University President Fellowship, which is very prestigious for his PhD in writing. And he also won the most prestigious award in the American Society of Photography and Motion for the Robert Cowell Memorial Fellowship. So, we're very happy about bringing that to OSU. And he's currently on sabbatical in Cornell University. So much in the box from Cornell compared to Hong Kong. So after he graduated from OSU, he did a post-1-year postdoc at Florida State University and moved to UC Davis. And then he moved to Hong Kong Polytechnic University since 2016, right? And then he was awarded tenure, promoted to associate professor last year. Very smooth journey. And Xiaolin's research interest, I don't need any paper to refer, so I know everything on his sleeve. So his research focused on developing novel remote sensing techniques to study the environment, including forests, especially here. We focus on forest change. And then he broadened his scope of research to urban studies. And he, when he was on OSU, he focused on daytime, daytime satellite data. And then he moved to Hong Kong because urban was likely nighttime. So nighttime light remote sensing is also very important remote sensing data source. So he also did a really interesting work in that aspect. So today his lecture is going to combine both day and night remote sensing data with dynamic. Actually, I just noticed his lab. He named his lab as PRIME, right? Remote sensing intelligence for dynamic Earth. Okay, so I think without further ado, let's welcome to give us.
Okay, good afternoon, everyone. So thank you, Wilson, so for the kind introduction. So I'm very happy to come back to come home. So it's 9 years. So this morning I just count carefully how many years I left OSU. Finally, I got 9 years. Okay, so Today I want to share my past research, and this is research about the day and night monitoring on land surface from space using satellite data. So even doesn't introduce my journey, but I want to use this map because I'm a geographer. So to show my track. So I born in Sichuan province in China. So I went to Beijing for my I spent 7 years in Beijing for my bachelor degree and master degrees. And then it's my lucky, okay, to have the chance to join this department. Spend 4 years, wonderful 4 years here to get my PhD degree. So after that, I go to Colorado for my first postdoc and second postdoc in UC Davis. And then I back to Hong Kong to join Polytechnic University as the assistant professor. So this map just shows the spatial information. So what's the time information here? So that year, the first photo taken by this department. So when I joined this department, I'm not sure if we still have this tradition.
Yeah.
Okay. So every a graduate student take a photo. So that's a younger me. Okay, back to 2010. So the second one is the photo taken by my current university PolyU. So when I just joined the department. So as an assistant professor. So the third one is the photo just when I got the tenure. So they say, okay, you get older, you need to replace your photo. So they ask me to retake the photo. So this is how the tempo and space and the geography, so we can see the information. Okay, so I have a lot good memory when I started here. So you say, I under supervision docent. So we go to the field work with the Kendra and the Dana and the Becky. So we spend 1 week to connect field data. So that's nice. And doesn't mention it's my lucky to get some award within this department. So finally, I successfully finished PhD and graduated in 2014. Okay, so back to my talk. Before my talk, I want to show two very nice photos. The first one is taken from the Victoria Peak in Hong Kong. So if you haven't been in Hong Kong, I think this is a very nice place to visit. So if you have chance to visit Hong Kong, so you can't just get to the Victoria Peak, so you can see the whole city. So you can see the beautiful harbor and the buildings. So this is the daytime photo. So we can see the land surface with different colors, the buildings, water, and trees. So if you are interested in urban environment, and you can find many information. So this is the same location, same viewing angle, but during the nighttime. So you see the information change. You can see the urban vitality, human activities. So the lights from buildings, from the roads, from the boats. Okay, so this means if we want to study the Earth's surface, it includes different systems, nature system, human system, urban system. So we need the data from daytime to nighttime. Okay, so I want to talk about why I'm interested in this such research, the background, and so because we only have 1 hour to talk about this, studies. So I just briefly introduce the new technologies I developed to improve our ability to monitor the surface. And I will give some application examples. So how we can improve our understanding of the dynamics. Okay, first, why we care about the change. So in the past 100 years, so the global climate change and human activities so have changed our environment, our land surface a lot. I just listed some example here, like the flooding, so with the global warming, and the fires, like every year happen in California, okay? And the drought in many countries. Drought is a serious issue. Of course, with the increase of population, urbanization. So if we want to understand this change and large scale, so which method is more efficient, effective? So then satellite remote sensing, because with the Earth's rotation, the satellite fly over the Earth and collect the data at any location. Okay, and any location. So with the satellite data, so we can observe the change at large scales. So I just list some of it, like the glacier change, like the agriculture system change, and the hydrology system. Okay, the river change. Okay, so a little bit background in case you are not, doing research in remote sensing field. So the daytime remote sensing. So what's the principle of daytime remote sensing? So as human beings, we can see the colorful world because we can observe the visible colors. Okay, yeah, like red, blue, and yellow, those colors. So, but as remote sensors, it can observe more than that. So this graph shows the spectrums of different, land surface objects, like from the clouds to the water, vegetation, okay, soil. So as human beings, we can only see this part. Okay, we have limited ability. So with remote sensors, so we can see more than that. Okay, a longer wavelength. So those information can help us to monitor the environment, land surface. So for example, the true color photo is like our eyes, like our smartphones. You can take photos. So you can see where is the vegetation shrub. So with the spectrum more than that variable bands, we can see more information. So we can see more information. Those cannot be seen by human beings. Okay. Okay. For nighttime, what is nighttime remote sensing? So as we know that during the nights, so there are so many artificial lights. So the lights from the street, lights from the buildings, lights from the transportation. So all these lights can be captured by the satellites. Then we can get that information to know what's going on the surface during the night. So here's one example. So this is a nighttime night data cover the whole China. So you can see where is the big cities, where is the rural area. Okay. So one more point. For the nighttime remote sensing, it can monitor the surface artificial lights, but meanwhile, it can provide observations of the atmosphere. So we can use that data to know the air pollution during the night. Okay. So I talked with some, people, they are not in the field of remote sensing. So they often ask me to do a lot of tasks. So do this, do that. So let's say they have like a problem in the crop, they have a problem in the transportation. Can we detect the information? So they think remote sensing is like seeing things from the God's perspective. So I think you can see such things from the movies or like FBI or like some guys to look for some bad guys and use the images, zoom in and zoom in, and finally find the vehicle, right? So like this one. But in reality, it's so difficult. So I give one example. Okay, I think even this happened many years ago. I think some of you know this big events. This is a very large earthquake happened in China. So back to 2008, caused many people, more than 10,000 people died. Okay, during that earthquake. So this happened is in the afternoon. Okay, it's 2:28 p.m. and the central government took quick response to this earthquake. So just after 2 hours, so the central government, the primary Wen Jiabao, okay, flew to the site, talk with the officers how to make plan to rescue people. Okay, it's very embarrassing for the remote sensing scientists in China. Why? So you can look at this photo. Okay, look at this table. So all the information on the table. So if we change another one, what's the information? This is a traditional map. They look at the map to say, okay, where is the roads are damaged, were damaged, where the houses were damaged. But this is a traditional map. So after 2 hours, why we cannot get the remote sensing data to see where the damage happened? Otherwise, so we should save more people. Okay. So this is I think it's a good example to show the remote sensing technology in reality. It's difficult. Okay. Okay. So my research in the past, you try to improve the ability, but I still cannot solve this challenge. But try to improve it. Okay. Okay. So the challenges in daytime remote sensing. Okay, most of the remote sensing data, more than half, is optical remote sensing technology. So what does it mean? So like today, it's a rainy day. So if you download the remote sensing data, you get lost. Okay, it's covered by clouds. So like those photos, images are all the images we can have over Hong Kong in 1 year, in 2015. That's all you can get. For example, if you are like a researcher in urban science, you want to study the land surface dynamics in Hong Kong. So there's no way you can get like a 1 or 2, clear image 1 year. Most likely in spring season. So you don't have data in summer, you don't have data in fall season. Okay. Okay, another limitation is the trade-off between the spatial resolution and the frequency. So here's the remote sensing data over Hong Kong Polytechnic University campus. So this is a 1 meter spatial resolution. So you can see individual buildings. You can see the roads, and even you can see the vehicles on the roads. So this is nice for urban studies because we want to know more details. But this data is not, firstly, it's not free, it's commercial data. That's not the issue if you have enough money, so you can buy a lot of data and your wish. But the problem is every 144 days, you can get one data. Okay, back to the Hong Kong case. So most likely you get lost per year because every 144 days, okay? So how about we improve the frequency? Like the famous Nansan data. This is satellites, run by USGS and NASA. So this is the frame. This is better, 16 days, but the resolution is 30 meters. So this is the same location, the polio campus. But can you see the individual buildings? It's difficult. But you can still say there is a building with right color roof, okay, in the middle. But it's okay. So if you just want to start something like a large scale dynamics. So how about daily? So if you want to study frequent change, okay, like some flooding, disasters, fires, this is a modest thing, 250 meters. The whole, of course, Tornado campus is much, much smaller than OSU. Okay, so if you use modest data, only 9 pixels, nothing left there. So you can't see much detail. It's not useful. So clouds and the trade-off between spatial and frequency, there are two major challenges for the daytime remote sensing. Okay, so since my PhD study, so I try to improve the ability to solve these two challenges. First, find where are clouds, how to remove clouds. Second, how to combine data with different resolutions and frequencies to improve the ability. Okay, so it involves different methodologies. The final purpose is to generate a frequent data with high quality. So this is a very technical part, so I will move very fast. Okay, so I just talk about the principle, how I do it, okay, how I finish it. So the first, how we identify clouds. So you may think clouds are easy to identify, but in fact, it's difficult because some clouds overlap with each other, so the color change, and some clouds are very thin, so you can still see the information under the cloud. So if you get the original data, so it's not easy to identify clouds. So we need to do some like a transformation to change the original data to a cloud index to highlight the cloud information and compress other information. Okay, then we do some automatic time series analysis to identify the real clouds. So we get the cloud mask. So based on cloud mask, the sun, clouds, and land surface, they have a geometric relationship. Okay, we can use that geometric relationship to predict the potential shadow area. So those potential shadow area can be confirmed by another round of time series analysis. So we can identify real shadows. So that's getting the real, mask. So like in Hong Kong, you downloaded all the images over 1 year. You just put all the images in that system. It can give you a mask automatically. Okay, that's the first thing we can do. And after we find the clouds, like one image, like 10% of the image covered by cloud, do you want to drop that image? I think you want to keep it. But that 10% of clouds will affect your subsequent analysis. Okay, then how to do it? It's better to remove the clouds. Okay, how to remove the clouds and other missing data? So we developed some like a geostatistical model to learn the information from non-cloud area, and also learn the information from the past data. So that's our idea. So we get the spectral clusters. For the spectral clusters, we can build the temporal relationship to learn the information from the past. Okay, but the learning is not 100% accurate. So there's always a residual. So that residual can be mapped for the pixel outside the cloud or outside the gaps. So for those pixels, we can build their semi-random model to this basically is the first law of geography. So I know everyone know first law of geography, right? But we need to quantify the law. So this figure quantify the law. So based on this, information, we can estimate the residuals. So of the temporal relationship. After with the estimation, we just add it back and we get the prediction. So that images without cloud, without missing data, then we can input that, take that data to our future analysis. Okay, so after we get the cloud problem, as I said, there are data from different satellites. They have different resolutions and the frequencies, how to combine it. So we needed the data fusion technology. So in the past, we developed different fusion technologies to address different challenges. So like the first fusion method is dealing with like data with very large scale difference. Okay, like in some very complicated landscapes to improve the accuracy. So the second one, deal with the faster chain, like here shows the floods. So like from one day to another day, the flood happened. So how to combine data from different satellites to improve the spatial resolution so we can accurately identify the flooded region, okay, to help people understand the damage, assess the damage. So this is achieved by data fusion technology. Okay, so that's the boring part. So we just give some example here. So this is done during my first postdoc in Colorado. So that project is funded by USDA. So USDA wants to know how the tropical forest responds to drought, to hurricane. But that region is also very cloudy. So they just collect data. So from the satellite, so they found the data like this one, okay? So any problem for the so for this one, they found it's very difficult to analyze the response of vegetation to drought to hurricane. There's so many like a cloud and recent data. So I just integrate all the technologies I talk about in one system, and we just put all the raw data in that system, and this is output. It's much better to study how vegetation responds to drought.
Yeah, that's more. Yeah, what is the thing something?
Oh yeah,
good. I was wondering, like, what kind of program are you using to create this example?
Oh, what the program?
Yeah, are you just using like a Python or something?
A very good question. So actually, I will show that in the end of my presentation, but I can talk this earlier. Okay. So when I was a PhD student, so I mainly use a language called IDL. So IDL is language, I think, program language, I think, widely used by remote sensing and the medical imaging analysis. Okay, so so my idea is, once I publish the paper, I always post my codes online to everyone to test, because so as yourself, you cannot test your algorithm in any large area. So I always open my code. Okay, but some people contact me, say they don't have the license of the IDL. Yeah. So they can't use it. So after like several years, I started learning a lot of language like Python. Then I always posted like two versions. So if you go to my website, you say all my like codes, algorithms with two versions. One is the original IDL, and a lot is the Python version. So then everyone happy. But it increased my effort, time to maintain the code.
So just for the information, our department we have IDL available.
Nice. Then you don't need
I
to
just switch from ODAS to NC, so IDL topic. For the safety license, private students are what we say.
Follow-up question. Is it streamlined? Is it on Stack Overflow? The code?
Yes.
Okay.
Okay, I think I can. Okay. So next part, I will talk about some examples. So in the past few years, we did how to use daytime remote sensing to solve some real world issues. So the first issue is about data duplication. So this is a serious environmental issue in loss channel. So there are so many lines, so lost during that process. But we are not very clear the specific process in the like a long time period, 20 years, 30 years. So we map it. Of course, you cannot map it without the technologies I just introduced. Okay, so the three technologies I talk about is the first step. So we use that technology to make better data. Then we can map the data in each year. Okay, like from 1987 to 2017. So 30 years. So, but if you just look at these images, you cannot observe large change. But we can count the vegetation pixels, okay, and vegetation status, health of the vegetation. For example, we can count the percentage of vegetation in this area. So you can say it's not stable. It has like generally speaking, it's increase with year. So what's the reason? So we investigate more. Okay, we found the reason of the vegetation increase in the data area is the agriculture. So because the more people, more population, and people need food, then they use more groundwater, okay, underground water to plant crops. Okay, that causes a lot of environmental issues. Okay, so this is a year example of yearly data. Okay, if we have good yearly data, we can do that. So next I move to a little bit higher frequency. We go to the seasonal data. So this is one good example is we did is about the tree species mapping in Ohio. So doesn't just mention that large project. So I involved in that project. So we did this survey, okay, to connect the samples in many years ago. So that's that's younger me, okay? Okay, so with the seasonal data, I don't show the details of how we map it. I just show the results. So with the seasonal data, so like the data cover the trees in different stages of growth, like in the spring, in the summer, in the fall, in the winter. So with all this information, we can improve the accuracy of tree mapping a lot. So we can reach 90% accuracy, and we can say where is the location of oak trees, where is the pine trees. Okay, then we go to a even higher frequency, weekly data. So if we can have the weekly daytime remote sensing data, what we can do? Okay, one example is the vegetation physiology. This is also related to human health. So I know Sandy is working on the human health. Okay. So this kind of information can help us to predict when is the flower come out. Okay. So last year we published a review paper, very comprehensive review paper, to discuss all the issues with such topic and what's the future directions. So with weekly data, what we can do. And I want to show another, not a review paper, it's a real example. So with the weekly data, what we can do. So in China, okay, with the increase of population and urbanization process, you can see such phenomenon. What's this? You can see the buildings, and just under the building, that's a farmland, crops. Okay? So because the urbanization is so fast, to occupy a lot of original farmland. So make the boundary between the farmland and the cities, become zero. Okay? So we know the urban system has the environmental problems like urban heat island. So that increase of temperature may affect the nearby crops. So this is a research question we want to investigate. So we use the weekly data to do this study, and we found some interesting results. Okay, in big cities, it did indeed affect the crop a lot due to the urban heat island, but not the small cities. Small cities are another story. I don't show the results here. So small cities are more affected by the nearby concrete surface. Okay, next the impervious surface, it has another energy balance equation. So it affects the nearby crops. Okay. So how about if we have daily data? This is one case study we did about the super typhoon. So this is one super typhoon happened in 2018. So it caused a large loss of the urban system, especially for urban green space. Many trees falling down, and some extreme case cause people die. Okay, so how can we quickly evaluate the damage caused by the typhoon? Okay, so here shows if we are lucky enough, so we have the image before the typhoon and after the typhoon, we can map it. So we can map the loss of the greenness. Okay, here shows the last column shows the results. So the red color means the loss. Okay, the loss of the vegetation in different parts of cities. Okay, so one more interesting application about the daily image. If we have the good daily images, what we can do? We can, find the direct rainfall events. So why we care about this? In the cities, you have many meteorology stations to record the precipitation, the temperature, moisture, but not in desert. In desert, we don't have weather station, or we have very sparse weather station. So you cannot know when the rainfall happens. Why the rainfall is very important? Because the vegetation in desert, they have very short life cycle. It come out today and die tomorrow, right? But it's very important for the Earth system. So can we capture the rainfall events using satellites? So if we have daily data, the answer is yes. So we did this study. We found the response of the vegetation in desert. The signal decreased with the time if the rainfall happens. So we can use this phenomenon, this principle, to design some algorithms to identify the rainfall events. Okay, here's the example. So we can map the rainfall in the data, even without any meteorology stations. Okay. The last example about the daily data is our last year project. So we got the funding from the Hong Kong government. So they want to know where is the illegal dumping happening. So it's difficult for this monitoring. So they use some cameras to put in different locations of Hong Kong, but it caused some privacy issue. So we use the daily remote sensing data. We can identify. I don't say all these points are illegal dumping sites. We call it a potential dumping site. Okay. So after we get this map, the government officers, they can go to these sites to verify it. It increases their efficiency a lot. Okay. Because they have some like a potential target to check. Okay, that's the daytime part. So let's move to another story from day to night. So night is a totally different story. It's a lot. There are many other challenges compared with daytime. As I mentioned, the daytime. So the energy received by the satellites most from the solar system. So the sun, emits the lights and reflected by the ground and received by the sunlight. But how about the lights? So most of the energy comes from the artificial lights. Okay? But it's not that simple. So during the nights, we have moons. And the moon is not stable, change day by day. Oh, sorry, night by night. Okay? So you have the full moon, you have the new moon, and the lights from moon will reflect by the ground and finally reach to the satellites. So that's a bias. Okay, you want to remove it. So if your target is study the surface part, and also the atmosphere, okay, interaction of the lights, and how to solve these challenges. Okay, NASA has a big team to solve these challenges. And another challenge is the viewing angle. The nighttime satellite observe the cities from different angles. So here shows one example. So if we observe this location from the laser view, most likely you can see the lights from the roads, from the top of the buildings. But if it's from a large angle, you see a very different, lights from the facades, from and a block. Some lights are blocked by the buildings. Okay, it's very different. Okay, I mentioned this environmental challenges, factors, and the viewing angle factors. All these combined together makes the nighttime data very, very noisy. So this part is a Beijing city. So during the pandemic, there are some people asking me to help them to see how the shutdown of the city affects the economy. So they say if they close all the shops, okay, and reduce the human activities, it can be observed by the nighttime remote sensing. So I tried, but the answer is no. Okay, so this is more than 1 year data in Beijing during the pandemic. So it's quite noisy. So for any pixel within the city, if you plot the time series like this, you cannot see clear pattern. So because of the issues I just mentioned. So there are moonlight, air source, surface albedo, vegetation, and Beijing is in the most part it has snow in the winter. White snow change the lights, and imagine. So if the snow cover the surface, it has a high reflectance. Okay, change the lights go back to the center. Okay, so in the past few years, we try to, solve some of the challenges by, doing some research like uncertainty assessment, angular effect modeling, and the color removal in the nighttime data. So first, we try to understand why the nighttime data has so large, variations, with time. So this is the raw data. So first, we can decompose the raw data into like a different, series. So some is seasonal series, and the angular effect series is most likely is show the time effects from the angle, and the angle fixed series most likely show the daily factors like the air quality. Air quality change day by day. So that is can be reflected by this series. So, and then we built a model to consider all the factors and in this model and to try to, fit in the data, raw data, and use that model to predict the time series, and the results turn out very good. Okay, so I just show two examples. So one is urban pixel, show the lights from the urban region. So the green color is the model prediction, and the green color is the raw data, very, noisy. So if we consider all the factors, it captures the and list, the large variations of the raw data. So there's another raw pixels. It also perform good, okay, to capture the large change. So after we understand these factors, the contribution of these factors, we can figure out how to, clear the data, okay, how to smooth the data. Okay, the second issue is the viewing angle. So we need to understand how the lights signal change with the viewing angle. So we did a lot of investigation in different cities and the global scale. So here I show one example in Los Angeles. So Los Angeles is a large city. So in a small part is a CBD area. So you can see there are so many tall buildings, and there's this part is like a small houses. That's a residential area, and we found in many cities, okay, in different countries they show these three patterns. So one pattern is a negative angular effect. So the lights observed by satellite reduce with the viewing angle. So if the angle increase, okay, like from this later view to this view, and the strength of the lights observed by satellite reduce. Okay, that's -1. And a lot of pattern is positive. With the increase of angle, the lights observed by satellite increase. And the last type is like a U-shape. Okay, decrease first and then increase. So this is the universal true, okay, in all the cities, we found this pattern. But the problem is how to explain this pattern using physics. Okay, so we propose this new physical model to explain the angular effect. So we consider the urban structure, 3D structure. So we summarize the lights are affected by three factors, major factors: blocking effect, visibility effect, and the surface reflectance. And then we developed some formula to describe this, the physics. And finally, we verify this model at different scales, from pixel to regional to city. Okay, so here shows the city level validation. So like 3 cities, one is Beijing, one is Los Angeles, another one is Hong Kong. So Beijing is very complicated, okay, because of the history. So many like old buildings, new buildings mixed together, tall buildings and normal buildings. So makes your aggregate effect is quite stable. You cannot see clear pattern because all the pattern mixed together. And for the Los Angeles, so even it has a CBD area, but the large area are residential area. So in the end, it shows the positive pattern. But the Hong Kong, everywhere is a CBD. Okay, so it's very dense city. So and the city level shows negative. So why we need to understand this effect? For example, if you are asked to investigate how the pandemic affected the economy, okay? So if you connect one data is in laser view and a lot of data is with large angle, you will find the light difference, and you may conclude, okay, this light difference caused by the pandemic. The answer is wrong. The answer is maybe 50% of the change caused by the angle, not caused by the real situation. So if we can use this model to estimate that impact, and then we can just drop that impact, and we can get the more accurate answer. Okay, the last one I'll just quickly go through it. So the lifetime data has more serious cloud issue. So I think like our department, there are so many professors that are in like research in climate or in like meteorology. So we know like during the lifetime, because the interaction between land and atmosphere, so it's more easy to have more clouds, okay, during the nights. So more clouds than the daytime. So how to do it? So we also developed some technologies to solve this challenge. So we validate the technologies with like cities and different location in the world. Okay, different global scale validation. So here is okay. We are not the first research group to do this. Actually, the USGS and NASA they released the product. So after they remove the cloud, so they also know this issue. So they try to give people better data. Okay, but their technology has a lot of limitation there. So we try to improve it. So here's the accuracy assessment. So this value is smaller is better. So this column is the results from the NASA official product. Okay, it improved a lot if we can better estimate the lights covered by cloud. Okay, so that's boring part. Go to more interesting part, application. So one example is how to find the change of the economy and construction and fine scale in urban section. Okay, so conventional map is quite static. You need to update, but a longer period, maybe 2 years, 3 years. So if you open some maps, you cannot see the progress of the construction. Okay. So this is one example. So if we apply the lifetime data, so even the major road network keeps the same. So the conventional map mainly show the road network. Okay. So even the major roads keeps the same, but you can see a lot in terms of the lights. So you can see how the colony developed in that region. Okay, the second example, how to monitor the urban vitality. For example, during the pandemic. So this is one example in Los Angeles. Why we did this in Los Angeles? Because Los Angeles have the Google access. So not in China, so we don't use Google. So Google released a data called the Google mobility. So Google mobility basically show the activity of human, okay, in the city. So it indeed show the change of the mobility during the pandemic. But if we use the nighttime data, if we use the raw data like the green color, not green color, it's yes, green color, orange data, it cannot follow the Google mobility. So if you use the NASA official product, it's a gap filling product. It has a lot of uncertainty. Basically, it's wrong. The official product. It shows the very stable. So if we can better predict the data, leased by clouds, then we can have a higher similarity, between the nighttime remote sensor and the Google mobility. So this is a very useful to some countries that don't have data of Google mobility. So we can still to investigate, monitor urban system change under some events. Okay, another example is the socio-economic issue. This is one example in Shanghai. So we can use the nighttime to find the ghost city. What is ghost city? Because the Chinese government, they try to develop the economy based on the house, okay, building new house. So, but that's so expensive. Not many people, actually live there. So that's called ghost city. Okay. So another example is the disaster. So if there are some hurricane, tsunamis, earthquake happen, so can we capture the damage or impact to the people? So this is one example, use the nighttime to capture the power outage. So after the hurricane, okay, to show how the power change. Okay, so I think it's time to finish my presentation, but I want to use a few minutes to talk about my research. So I can't cover all the research during the last two parts. So because I'm come here to seek more collaborations in the future. Okay. So if we look at remote sensing research, this is a whole chain. Okay. We start from the satellite. So we need to understand the remote sensing physics. Then we can understand the raw data. So this is the first part. We can do some scientific research. So understand the signal recorded by the satellite. Okay, how the lights interact with different objects on the surface. Okay, so after we understand raw data, so the raw data has a lot of problems. So we need to do some data processing, develop some new algorithm. So that's get the remote sensing data product. So USGS and NASA and NOAA, they release a lot of this kind of remote sensing product. Okay, of course they develop a lot of algorithms to generate that product. So that's the second part. We can do research, and the third part through the collaboration with the other fields like the health, okay, urban science, agriculture, we can apply remote sensing data to solve some scientific or societal questions. Okay, so that's the third part. So in the past, about 10 years, so I did like a research and also developed some proposals, get some research grants in all these three parts. So, so that's so a summary of my past research projects. And for each part, we got some like funds. So the Hong Kong RGC is the Hong Kong Research Grants Committee. So that's similar with the NSF here. Okay, so it's a supported the general research idea. So NSF says the NSF in China. Okay. Okay. So I have several projects, ongoing projects in like three different directions. One is the data integration. So besides USA, other countries in past few years, they compete with each other to develop more satellites, launch more satellites. I don't think it's a good idea. Okay, so every country they try to like launch new satellites, connect more data, but how to use all data together to make our ability stronger? So that's the question. Because the data is from different standards, is from different person code, from different sensors, from different bands, then how to integrate. So I have some research projects focused on this part. And second part is because now I'm in Hong Kong, right? So if you want to get some research grants, it's better to develop some proposals related to Hong Kong. So that's the urban environment monitoring. So like nighttime is a part of it. Okay. So how to monitor the urban system. And last part is the carbon modeling and vegetation monitoring. So this is during my PhD, I already did some research in this topic. So I continue doing some research and have PhD students focused on this part. So and now the carbon is also a very important issue. Okay, it's not in like a developed countries, also developing countries, or in anywhere. Okay, so people talk about how to reduce the carbon emission, how to reach the carbon neutrality. But I know I don't truly believe we can get that. But we need to do some research. So it's difficult to every country to get the carbon neutrality in the end of 2060, right? Some countries 2050, some countries 2040. I guess some countries will give up if they set the standard too high. Like if they want to reach the carbon neutrality in 2030, I think it's very difficult. But I think it's worth to do some research to see how we reach that goal. So even it's very challenging, but it's good for our future. So this is my personal opinions, maybe not accurate. Okay. Okay. So with this research, I'm open to collaborations. So from different disciplines, different fields, like environmental science, like air pollution. So the remote sensing can contribute. The urban science as transportation, okay, and the social science like housing issues, equality issues, and the sustainable development goal. Okay, that's also I think it's a very hot topic currently. Okay, many countries they have different plans to reach the goal, but how to realize it? So there's a long way to get that final goal. Okay. Okay. So this is a real conclusion. Remote sensing is very effective for monitoring the environment change. Okay, across different spatial and temporal scales. So I don't say remote sensing can do everything, but it can do something. Okay. And its timeline is very limited. Okay, it's limited by the standard technologies and observation conditions. So this is why after the earthquake, we cannot get a map from the satellite to show the damage. This is very challenging. So image processing algorithms can lift some of this limitation. So it's better than nothing. So we can do something. Okay. Okay, applications. I think I want to emphasize this part. So applications should consider this uncertainty from remote sensing data and technologies. So this is I think it's a big gap between like two groups of people in remote sensing field. So one is focused on remote sensing physics and data processing. Another group just focus on application. So there is a gap. So I saw many papers, even the published in the very top journals. They just use some like modest data, like some modest product or some like a data released by LoA to do some like global studies to get some very fascinating results, very good results, and just write papers. But we need to know this data, this product has some uncertainties. So those uncertainties maybe make your results biased, maybe by not 100%, maybe 50%, 30%. So maybe your results is the overestimate or underestimate. So I think these two groups should work together, okay, to make the remote sensing data, better and easily understand and higher quality and more accurate. Okay, this is a very hot AI, okay, deep learning. I would say, I don't know the situation in USA, but I would say in China, in Hong Kong, half of the PhD students in remote sensing, they use deep learning algorithms to map the land surface, to estimate the carbon. So everything they can use deep learning. Okay. So I don't see AI, cannot do it. So I think AI may help remote sensing study, but we still need to focus on the physics part. Okay. And AI is limited by the sample. Okay. AI needs a large sample. And I found in remote sensing studies, the sample quality is very bad. So even some people publish data, say they connect like a 5 or 2 million of samples. But if you download their samples to check their labels, check their information, you can find a lot of errors. So the sample, I think, is the bottleneck for AI application in remote sensing. Okay, many new remote sensing data come out, so there are many challenges, issues. So this is good for PhD students in remote sensing. They always find a new research questions because each year we have new data. So I know in USA there is a new satellite. It's very useful. It can monitor the it's called SWOT SWOT. It can capture the high resolution water topography. Okay, that's very useful. But we don't have that data back to 5 years, 10 years. But it opens a new direction in the remote sensing field. So we always very excited to see new satellite launch. So we have new research topic. Okay, so my research funded by some agencies, and I thank some PhD students their contribution to my today's talk. Okay, some of them did lifetime remote sensing, some of them did daytime part, vegetation, agriculture. Okay, one more thing as they asked. So the codes. I really hope the technologies can be used by many people and can benefit the research and studies from different fields. So once I develop the technology, I always post the codes online so people can easily use it. So besides the codes, I also post the data I used in my paper. So any people, if they are interested, you can compare their technology with mine to say the limitation or how to improve this technology in the future. Actually, this is a very good thing, okay, for research. So as I mentioned, we have two versions. So the traditional version and the new Python version.
I know MATLAB.
Oh,
Just kidding.
okay. I can't learn all the programming language. Okay, thank you.
Very comprehensive, very informative part. Questions, I think based on our current tradition, we will let our graduate students ask questions first.
I have a question regarding the cloud mask. Did you assess the accuracy and how did you do that? And the second question, are these codes are applicable for hyperspectral remote sensing? Because multispectral remote sensing is not satisfying all the needs. For example, in agriculture, you cannot even differentiate wheat from barley. So if we use hyperspectral, may we use the same approach?
Okay, so you asked a few questions. So I think both are very good. The first question, there are two ways to validate. Okay, USGS has a cloud mask product. So that product, I think the masked by some expert. So that's open to everyone. So when we develop some new algorithms, we always use their data to validate. So that's you can just Google it. You can find that product. So besides that, we always find some students, graduate students to digitize. First, we train them how to identify clouds from the images and ask them to digitize the cloud. And for my research, I asked three graduate students to digitize the same images and get the average of the three students and the ground truth. There's no way to get the 100% accurate ground truth. That's the only I think an effective way we can generate some validation data for the cloud mask. So your second question for applied application to the hyperspectral. So the hyperspectral, there are two issues. One, the hyperspectral, we are not easy to get the time series data, multiple temporal data. The hyperspectral, most likely you can get a simple data. So some cloud detection algorithm cannot be applied because it's a single data. The second, hyperspectral cloud detection, it has more information to use. So if the bands cover the water absorption regions, and you can use the water cloud to detect cloud. It's a very important information. Why? Cloud is higher than the ground. Okay? For example, ground is here, cloud is here. So for the water absorption bands, so if the bands touch the ground, the absorption is very strong. That means the pixel is dark. So if there are clouds, the absorption is lower. So that means the pixel is bright. So that band is very helpful. If you have the single hyperspectral data, you can use that band to detect clouds. Okay. Thank you. That's called a water vapor band.
You mentioned so you're right, there's a lot of sort of new studies that take maybe global or large regional data sets that are then used, using remote sensing that are then applied towards the modeling studies, for example. And you sort of suggested there's a gap where those data aren't necessarily being scrutinized and we're not really assessing the uncertainties in those large data sets. On the order of 30 to 50%, you said. And I was wondering if you could give an example of Yeah, what do you mean by like there's uncertainty?
Okay.
50%.
Okay, I understand your question. You need a real example.
Yeah.
To show. Okay, one good example is the tropical vegetation.
Okay.
Okay. You know, the tropical vegetation, most of the vegetation are evergreen. That means you cannot see much change. Okay, with the time. Okay, but 10 years, maybe more than 10 years ago, there are many people they use remote sensing data to study the vegetation dynamics in the tropical region. Like for example, the phylogeny, what is the impact of the drought. So the dry season and the wet season, so the vegetation has some change. So they are very excited. Say, okay, we see the change from modest, but there's a scientist, okay, publish a paper in Nature to argue that. So if we correct the angle of modest, that change disappear. That dynamic, okay, process disappear. So that change, drop, and increase caused by the viewing angle and the solar angle. You understand? That's in remote sensing, that's called BRDF effect. So that professor, after they apply the BRDF adjustment to the data, all the information change. Okay, that means the previous studies, all of them are wrong. So I think this is a good example to show we should pay attention to the data because data connect different day and the sun has different angle from winter to summer. And the modest has a wider view. Sometimes the modest is from later view, sometimes the modest from the off later view. So if you consider all the observing conditions and build a model to adjust this effect, and the time series change.
This is not so much for like categorical data with kind of map features, but instead for like
yeah, you're right. So more like we call it quantitative analysis. So you can find that paper. So I just talk about how they argue. We need to pay attention to the image process.
I have some questions about the relationship between the urban and crop. It seems like different urban sites have different influence on the crop. So I have two questions. The first question is that how do you quantify the influence of urban on crop? The second is there any physical process about this relation?
Okay, so I thought you asked two questions. One is how to quantify the impact. Second, how to explain the results. So I didn't show many details here. So I go back to the figure. So here. Okay. So in this study, we select a typical crop as our target, research target. That's a winter wheat. Winter wheat means we plant the wheat in the winter. Okay. So when snow happens, so the green part die. Okay. In the coming spring, when the temperature increase or get warmer, so the wheat come out again. So that's like a two peak. The first small peak is in the winter, and the second larger peak in the spring. So we use that like a growth cycle to get the timing point of the vegetation come out again. Okay, that important timing is our study target. So we see how the urban change that timing. So it's a 5 days earlier if we have a large city there, okay, or it's like 10 days earlier. So we can compare the same species, okay, the winter wheat at different sites, and use remote sensing data to get the timing point, and use that as our target to investigate the urban effect. So that's your first question. So this second question, you need to understand the physiology of the vegetation. So how the vegetation responds to the micro environment, like precipitation and temperature. So we need to understand the domain knowledge from ecology part or biology part. So we use that knowledge to explain why the winter weight come out earlier in the large cities. So and we also explain how the heat, okay, in the large cities spread to the surrounding area. There is some like a process. How the warming temperature, okay, from the city center to the other part, and what's the speed of that spread. So all these together, we can explain the results from the remote sensing data.
So the result is for a certain class. So if they're different, and we'll have the different response.
Very good question. So I found that there is a large problem in the past few years. Many people publish papers about how vegetation responds to urban environment, and they publish in like PNAS or some very top dollars. They don't differentiate different species. They consider all the vegetation as one. So what's the problem? Most important issue, I think, is the difference of the species in the urban and in the rural. So they say, okay, the urban vegetation the leaves come out earlier than the rural part. So this, like 10 days earlier, is the impact of the urban heat island. But if the urban region, we plant like oak trees, but in the rural area, we plant maple trees. They have like an intrinsic difference, right? But this difference may be not caused by the urban heat island. It's just a species difference. So they don't consider this difference. So this is why we only select one species to avoid this impact.
Okay. I was wondering what is the temporal resolution for the treatment data? Because you're treatment data some have written 144 days, and then 60 days, and there's 1 day.
So the ideal situation, the frequency of the fused data is match the best one of the original data. So if you have daily data fused with the 15-day data, and the fused result is daily. Okay, match the best one.
Have you tried fusioning nighttime data with daytime data?
This is a very nice research question. I think you can try. I never tried that, but it's a good question. So fuse daytime and nighttime. Because they have different, information. I think I have my own opinion and suggestion if we want to do this. Don't do it at the raw data level. So do it at the decision level or feature level. So that means the daytime show some information, nighttime show other information. Maybe combine can get a better information.
I have a follow-up question regarding this one. I see that there are different cities. Then how can you disentangle the factors caused by urban heat island, or it's just a broad environmental difference?
When we select these three cities, we control the environment factors. So they are in the same, so climate zone, and they have like similar like topography. So we try to control the environmental factor, but you are right. That's still a problem.
They're in the same province, right?
Yeah, same.
So what would be the temporal scale like? Like within like 1 or 2 years to see the change?
3 years, because we need a high resolution data. When we publish this paper and we only have like 3 years of good central data, so we only have central data since 2016. So but you are right. It's better to investigate the long term, like 20 years. But we can't do it because we don't have data.
Thank you.
Last question. You verified, no questions from faculty members. Last question for you.
So from what I've been seeing, there's been a move from just single package systems where it's one satellite to constellations, multiple like few satellites. Have you or your team worked with data from constellations like multiple small satellites? And are there any challenges with working with data from those kind of systems?
Yes, I don't show this work in today's talk. We did in the past 3 years. We work with the Telescope. The Telescope is as you said, it's a new satellite constellation. That means it's more than 100 small. We don't call it a small satellite. It's a qubit satellite, micro satellite. It's like this size. You launch this size to the space and 100 and observe the data. So you can imagine the quality. Okay. Okay. A little bigger. A little bigger. Okay. So one qubit is 10 centimeter by 10 centimeters. 10 centimeters.
I think you do have a slideshow telescope somewhere.
Okay.
You use telescope in your.
So as you said, the quality is not good because you get all your pay, right? So it's cheap, but
it's free for students.
So there are several issues. First is the geometric consistency. So the different microsatellites, they connect data. You cannot stack them together. So they have the geometric difference. They have geometric difference. The geoposition accuracy is low. That means you connect like one satellite connect data today, like overseas. Tomorrow is a lot of satellites. So if you overlay them together, they are shifting. So you need to do it. How to correct it. So there are many issues. And the spatial response function is very bad. That means if they call the spatial resolution is 3 meters, in my personal opinion, I think it's 10 meters. Okay, it's the quality is similar with central. But that's the trend. I think in the future, we improve the hardware, right? Keep the lightweight, but improve the ability. Then that's become much better. That's the future. Then people don't need to use my fusing technology, right? So I'm happy to say that because that can really help this issue.
All right, 35, 45. So let's give
and also welcome all you related to Hong Kong. Okay, that's a beautiful city.
Great talk, man. Thank you.